this is a web address for the live stream of our lecture and classes broadcasted on time. So if you have some problem not coming to this classroom, then you can watch real time. Okay. So coastal processes and ocean observation. So this is the book we are covering, and then this is a chapter 4. I will cover first part of this one, wave reflection and wave. So this is the more detailed description of our coverage today. Hind casting, secondary flow, Ekman spiral, upwelling, rip current, global currents, loop current, and gyrus. Special terminology, right? Ocean also have a special terminology too. I will cover this, and Ingyu covered the later part of this slides. Hind casting is another reverse opposite way word of forecasting. Forecasting can be a prediction, right? Prediction. But we don't know until the time elapsed. But hind casting is trying to simulate the already happened situation, event. So reverse way. So hind cast is a way of testing a computational model. In that term, forecasting is the same. We also use mathematical or computational model for the prediction or forecasting. But hind casting is something like a back testing rather than front testing. It's estimated input for past events. Right? We already have, right? And into the model to see how well the output matches the known event. Forecasting, say weather forecast. Tomorrow there will be a raining or snow. Right? It can be a prediction for the weather tomorrow. We call this a forecasting. But yesterday there was a rain, right? And also wind, high wind yesterday. But I have a prediction model, computational model of weather. Right? Somehow is probably fluid dynamics involved. Right? So can I use that model to calculate the result of, how can I say, hind cast forecast back whether the model produced raining and windy yesterday, right? To check my computational model. Forecasting is similar. Say tomorrow there will be a snow, I forecast, but we will see that whether this forecasting is correct or not, right? So similar, but a small difference. And collision simulation of a car. See, this is a collision test of real car, right? Real car. This one, real test. Real car and dummy model, airbag, right? But this one is a simulation model, computational model of same experiment. Right? And then they are saying, which one is which one? Probably one of them is simulation, the other one is experimental. Right? Curve, color, and it shows that they are almost same. So computational model is very good, right? You can say this. See once again. How can I try again? This one, all right. And time, see the moving tablet, the time is moving, so the same shape is done this way. So almost same. So this simulation is very good, right? You can say. So then what happened? Somebody saying that we don't need the experiment anymore because computational prediction is very good, simulation is good, right? So anyway, this one is moving together in this way. So the prediction, forecasting, and hindcasting. But this one, they tune the parameters using the experimental result of many experiments so that they can predict well. But for the forecasting, may be different. So I want to show you this kind of prediction and forecasting is important for the engineering and also science too. Secondary flow, when you drink coffee or tea and you put some leaves or sugar, many times you put sugar, right? And then to make a meltdown, you rotate the water. Right? But if the water is not warm enough, or it may be cold water, then sugar is not melt easily, right? And then sugar is collected inside, in the middle, like this one. Why? Why this way? Because I rotate this way, but sugar is collected in the inside. We call this is a secondary flow. See this, I'm rotating the water in this way, but the other way, the water is circulating in another way, vertical direction of rotation. We call this one as a secondary flow. This one is a primary flow, and that one is secondary flow. There's a video, but this one is made by Japan people, so that I can shut down. Nobody can understand this one, right? So, okay. Well, you can read this one, right? So when they start some debris or sand is located all over the spread out, right, in this way. But you can see this, the person is rotating the whole cup, right? And then we see this, the sand on the bottom is moving toward the side of the body of the cup, and many times it did rotate, and at the end of the slide you can see that they stopped somewhere. Where is it stopped? Okay, this way. Right. The basin is stopped by hand, the brake, hand brake, right? Hand brake. And then the sand or sugar is moving toward the center of the basin or bottom flow that we call the secondary flow. And finally, the sugar or sand is collected at the center of the basin. Same phenomena as the curve. Because now the curve is stopped, only water is rotating, right? And because that is the primary flow, primary flow. primary flow, and then secondary flow is the other orthogonal direction. Right? This is a sink vortex apparatus. This is a water basin. You wash your hand and wash in the morning. You toothbrush and wash your hand. Then basin. The water is flowing in this way. You may not notice that kind of direction of water flowing. But when water is full and you plug out and water is draining, but the water is rotating, right? In this way. You may remember this, right? That kind of thing. Why this should be go direct to the sink point, but it is rotating and going sink down, right? That we call the secondary flow. So why it is working? Because of the rotation of Earth and other things. So that is the same theory behind, but at the ocean surface, this is the ocean surface, and wind is blowing in this direction, and then water is moving toward in this direction. We call this is a Ekman spiral. Probably this is a personal name who find this kind of phenomena. But this one is also same as again secondary flow. See, wind is blowing this way, and surface current is in this way. But net water transport, this is a whole volume of water, rather than a surface movement, because this is a depth of the water. As water depth is going on, water direction of moving is changed, right? So that altogether in terms of integration of the depth, the net water transportation of the volume, you can calculate in this way, total, because they are different ways, moving different ways. So this one called they are Ekman spiral in the northern hemisphere, and the depth of the movement is about 100 meters. But same again, this is a secondary flow, phenomenon of secondary flow. And once again, the coastal upwelling and downwelling. See, water surface, the wind is blowing this way, right? We can assume sometimes it blows in this way, but when water is blowing in this way, say in this way, and then surface water is moving, net direction is in this way, orthogonal to this wind direction. Right? Surface water is 45 direction, and the other one is moving down, so that altogether it is orthogonal direction. So water is moving toward the deep water side, right? Then there is a void. Water is empty there. So how can they fill this empty place? The water is going up in this way, from the bottom to the top, because the water is moving toward the deep water. So this one we call the upwelling. Water is going upward. Right? And when wind is in reverse way, then water is going in this toward the land side. Then this way the water should go down, because more water is coming to the beach. You need to move some water here, so they should go escape. So that you can imagine some movement of waters, mixture of waters, because of this movement or directions, and mainly because of the wind directions. So this is upwelling, and we call it downwelling. Same one, right? But this one is different direction. the previous one was wind is blowing along the beach, but this way the wind is blowing from the land side to the water side. So wind is blowing in this way, right? In this way. No, in this way. Here, in this way. In this way. From the ocean to the land, then surface current is going orthogonal direction to the wind. Right? And then here another kind of upwelling is coming because of the surface current. See, water is going toward the sea, and the other way is some kind of small mountain inside the water. Then water, because of the barrier, water is coming on this. Right. And then this is another one of circulation. A secondary flow and tertiary flow. Because wind is blowing, water is go the other way, so that there is water is collecting, so that water is circulating in this way, or the other way. So that's why we see this kind of streak. This is streak. And they call, this is a circulation here, circulation. So upwelling and downwelling is combined together. So there are complex motions around the sea, coastal waves, because of the wind and land. And rip current. Rip current is very dangerous thing. Sometimes water is moving in this way. Even going, incoming wave is coming into the beach. Some portion of the beach, there is a water coming toward the sea. Then if somebody is floating around here, then it can be dangerous. He is moving toward this deeper water. We'll see this video again. This is an English video. Sound is up. But these ocean phenomena are actually just currents. Rip currents are narrow currents in the surf current and move quickly away from shore. A typical rip current ranges from 50 to 100 feet wide and can extend 100 yards or more offshore. It can reach speeds of over 5 miles per hour. That's faster than a Olympic swimmer. That makes them dangerous and potentially deadly. And scientists want to learn more about them so we can better forecast when and where they will form and keep beachgoers safe. Here's what we know. Waves don't have to be huge for a rip current to form. 2 or 3 feet is all it takes. And the weather doesn't have to be bad for a rip current to emerge. They often occur in the night days after a storm. They're usually strongest in low tide, but can form at any time. Rip currents often form where sandbars are near the shore. They occur at lakes or channels in the bay. They're often difficult to see, but you can spot them in areas where waves aren't breaking, or where there's foam, seaweed, or discolored water being pulled offshore. It's easier to see rip currents from higher up, such as from the beach access of lagoons or lifeguard spots. Rip currents are a hazard to beachgoers, but by knowing the dangers and what to look for, you can avoid being caught in a rip current. The weather forecast when gets faster than the Olympic swimmer. See, the speed of the rip current is faster than Olympic swimmers, so it can be dangerous. All right. Questions? All right. And then other kind of currents. Where is the land side? This is the land side, right? And water is moving to incoming wave direction, but also there is an underwater water stream, or they are saying current strength distribution. Because of the water is incoming, there should be some motion in both way. so that wave is incoming, water current is there below the surface, and also sometimes there is a lip current. The lip current is going down into the deeper side. So some of this one, right? And this is okay. Energy escaping shoreline out to the deep sea. Also, this is a wind breeze. When the daytime, this we already see this when you are elementary school. When the sunshine is there, daytime, land is warmer, so that air is going up in the land side, so that wind is blowing from the seaside. Right? And nighttime, land is colder than sea, so that water at sea level is higher temperature, so air is going up in this way, and then wind blows from the land side to the ocean side. Right? We already see this one when we elementary school. This one already you see this the other day, so I skip over this. It was picture coming from NASA, right? Space Flight Center. They catch many satellite images and then make a video out of these snapshots to make a film, moving film. Oh, this one is a very similar one, but you can see the strength of that. Right, this one. You can see that this is a picture coming from the different months of the year. The year is count is changing from June, July. And you can see the continent of Africa here, South America, South Pole, and you can see the current, strong current. And because due to the colors, you see that the stronger one is more bright, right? Australia, and then you see some pictures for the India is coming. I want to shoot this one later. Okay. Okay, then right. Right. And this one is another one. Probably near North America, and where is it? Cold water. Is it North Boston somewhere? New York, Washington somewhere. This is Florida. Right. And they are trying to see eddy formation of mesoscale. Mesoscale means a middle size, not just before we see the current of bigger size, right? Global scale, big current. But here they are saying mesoscale, not small, medium sized. And eddy means rotating because of this is a week 1, week 2, week 3. And because of the cold water and warm water of the ocean, Gulf Stream, and they are moving, and then it comes with a separated out cold island water rotating. Warm water is rotating because of these actions coming from Atlantic Ocean and cold water from the North Pole. Right. So this is similar one, mesoscale inside the Gulf of Mexico. There are so many smaller, medium size loop current is coming, and then that kind of thing create. This is a simulation of Gulf of Mexico too, right? And then how the rotational motion of water is forming because of the global scale current and also interaction between cold water and warm water. And then this is also mesoscale to sub-mesoscale means smaller, right? And also this one is a computer simulation rather than a real picture. Okay. So they say a vorticity, oceanic vorticity, and surface motions rather than deep water. And this is gyrus. And where is it? See, this is India, Korea, Japan, Africa, North America, South America, and there is a well-known 5 big places where the garbages are collected there. So this is, I guess, this is final slide for me. I'll show you one video on Gyrus. Right, this one. Sound is good. Okay.
A gyre is a natural phenomenon. A gyre is simply a rotating current system that's comprised of Earth's rotation coupled with currents and flowing winds. So it's essentially like a massive whirlpool, a vortex in the oceans. Say a massive floating plastic from California in the North Pacific Gyre can take 10 years to make a rotation from California to Japan and all the way back.
What we have found is that these plastic particles are not just in the North Pacific Gyre, they're all 5 tropical gyres, and all these gyres have several garbage patches in them. 8 garbage patches total from 5 gyres.
So that was our inspiration to start the 5 Gyres Institute. So look at this plastic pollution issue on a global scale. And we try and show the world this is an international problem. These plastics are coming from every continent in the world, and solutions have to be on the international level. When I first heard this talk in 2001 from Kathleen Moore, I heard a description of an island of garbage that people were calling the Great Mosquito Garbage Patch. In the media, it was described as a Texas-sized island.
It's really hard to quantify how much plastic is floating in the world's ocean. These garbage patches that exist in the gyres, they're elusive, they change shape, they move around. You can trawl for 10 hours straight, you'll get a handful of plastic. You go back in 10 hours more, you get nothing.
So it's essentially like a plastic soup of all of this disposable waste that we create on the land masses from California to Asia, Canada, Mexico, enters this North Pacific Gyre and gets swept up into this accumulation point.
Islands in the gyres, we discovered, are the natural nets for trash at sea. It's impractical to try and scoop out trash out of the ocean. What we can do is basically wash ashore. So to clean the gyre, clean the beach, clean the watershed, clean the street, as closer to the source is a better way to solve the problem of plastic.
Okay. That's it for my part of slide set. And then we move on to questions. No questions. Then Inge is coming for his lecture. 이 스크린이 안 보니까.